So welcome everybody to this CSDMS Community Service Dynamics Modeling System webinar. My name is Irina Overeem and I'm part of the CSDMS Integration Facility team here at CU Boulder. And many of you are familiar with these webinars that are fairly informal, but informational about activities that go on in sort of the modeling of Earth service processes community, tools for modeling, and try to bring people together that are interested in development and building of cyber infrastructure, and sometimes a bit more science oriented, sometimes a bit more technology oriented. And so today we're pleased to have two speakers, Robert fkorn and Andreas Dedner. And Robert is at the University of Lund and Andreas Dedner is at Warwick University in the UK. So it's late in the day for the two of them already, or a little later than for us here in the United States. And they will be giving us some information and maybe a little bit of history of a long existing numerics environment. It's called DUNE, the Distributed Unified Numerics Environment. And it's already been in development for almost 2 decades, not quite. And so I found papers of this C++ part of the code, but there's been quite a bit of recent development in the last decade to connect that to Python frameworks, etc. Also, it's gridding capability, etc. And Robert and Andreas are going to explain a little bit to you how they've started, maybe the history and capability of Dune, but also how they started to connect this a bit to LandLab, which is of interest to a lot of the people in CSDMS that are doing more simple Earth service process models. So with that, thank you for doing this. It's always a pleasure to have speakers and sort of people share their tools and their information. And I'll give the floor to you, Robert and Andreas.
Thank you for the invitation. I hope you can see the slides.
Yes, we see the slides quite all right.
Okay, good. So thank you for providing the opportunity to present at your webinar. My name is Robert fkorn, as you said, and my co-author here is Andreas, and we'll show you a little bit about how we solve PDEs with a software framework called DuneFem. So today we'll briefly talk a little bit about discontinuous Galerkin methods, which is one method that we use to solve partial differential equations, then a very brief introduction to the software framework, and then how we envision to couple our code with LandLab for potential future collaborations, etc. And in the end, of course, we have some examples prepared, and there is, of course, room for discussion. So in a lot of our research and application, we look at quite general advection diffusion equations of that form. So we have some unknown u, some advective term here, some diffusive term, and a potential source term. And if you think of one of the simplest example, linear advection of 4 tracer variables in 2D for a given velocity vector v, then these functions f, c here, f, v, and s is of course 0. This could look like this. So you just advect the tracers with the given velocity, and you might have some diffusion coefficient epsilon here. Very simple. So this is how this could look like. And we will walk through this example here today. Before we look at the example, here's a very, very brief introduction into what discontinuous Galerkin methods actually are. So we, for that example, forget about the other terms in the equation and just look at the advection term. And to then define our discontinuous Galerkin method, we select a space of a discrete space which consists of functions that map from our computation domain to, let's say, R, or R to the power 4 for our 4 tracers. And these functions consist of polynomials on each element in our discretization grid. Here you see an example of a discretization grid consisting of triangular elements. And so once we have our space, which is usually quite simple to create, we can create a discontinuous Galerkin discretization by multiplying our equation here with test functions phi and then applying integration by parts, which then gives us these two terms. We have an element integral where we put the gradient onto the basis functions by integration by parts, and then we get some integration over the element boundaries where we introduce so-called numerical fluxes that are well known from finite volume methods. And here we just reuse standard finite volume fluxes. For our tracer example, we'll simply use an upwind flux. And to not bother you much more with these details on the method, so if you select piecewise constant polynomials here, polynomial degree 0, then you see that this term here, it vanishes, and we also don't have to multiply with the basis function actually, because they're just going to be identical to 1. And then we, in this case, recover our standard finite volume scheme, for example, as implemented in LandLab in the linear advection module. So this is exactly the same. And the nice thing here about these DG methods is that they can be of higher order and they have the same stencil as these very simple first order finite volume methods. And once you have created your spatial discrete operator here, your DG method, then you can apply standard time stepping methods. Of course, this here involves by somehow inverting the mass matrix, which in the case of DG methods is very simple, because you don't have to invert very large matrices. This can be done by element because of the discontinuous basis functions. This is quite efficient, and once you do that, then you can apply standard Runge-Kutta methods for solving or for getting the time discretization done. Here's a very simple third order 3-stage strong stability preserving method where you simply have to apply your discrete operator multiple times. A nice feature here is that these methods are locally mass conservative, which is, for example, a reason that they have been used in many fields, such as atmospheric flows or just standard CFD methods for compressible flow. There, these methods are quite popular. Furthermore, we have quite a high data locality due to the small stencil, but the high number of unknowns per cell, which is quite suitable for modern hardware. And these schemes and the setup here is also quite suited for so-called Jacobian-free Newton-Krylov methods, where you could envision a matrix-free implementation of this operator L. And this, again, then is quite suitable for current day and coming hardware. So this is actually all I was going to say about discontinuous Galerkin methods. Let's jump into the Python bindings for our DG module here. So in this case, we're interested in a slightly different approach than what you might see from other quite similar software packages, such as Phoenix or Firedrake, where you would, for example, implement a weak form. In our code, at least in this tune-fem.dg code, we don't do that here. We describe the strong form, which means that we're actually implementing the functions fc, and if the diffusion coefficient is not, if this is not none, then we also describe fv. And if you recall, so fc was simply the outer product between our vector of tracers with the velocity, which is written in this quite nice form here. So we create a matrix which in each row contains the corresponding u times velocity component. So this is how the Python code here looks like. For those of you who don't know this syntax here, this is based on a language called the Unified Form language, which we then use to generate C++ code out of these Python constructs. And of course, here corresponding the implementation of the diffusion method also quite simple. So this is already a model, only has a couple of lines, which allows to steer our discontinuous Galerkin solver for this kind of equation. And once you have written your model, you could run that. For example, here a standard test case for a linear advection problem, the solid body rotation, where you have these kind of different shapes of objects here, and then you rotate them through the domain. And of course, after couple of rotations, you want the objects to stay exactly the same in shape, but this rarely happens. Here in this case, you see that we need quite a high resolution here with adaptive grid refinement to get the same shapes. And in the left picture, actually, it's very difficult to see here. I apologize for that. We also have some overshoots, so the solution of this problem doesn't stay within the bounds, but we can achieve that by applying a limiter. And then the solution is exactly between 0 and 1. And these kind of limiter techniques can also quite simply be made use of by adding, for example, here, lower and upper bound to our model class, or some function describing physicality of the state. So in this case, ensuring that the function values are between 0 and 1. And for other limiter purposes, also defining a jump. So all of this description of the equations and how to kind of define the models and use the code is presented in a not so recent paper anymore from Andreas and myself, where we explain how to use the code. And in our current research, actually, we use exactly that implementation and the Python way of defining models to look at atmospheric flow test cases here, a so-called rising bubble test case with the time explicit solution on the left and the time implicit solution on the right. And in recent works, we have been interested in creating preconditioners for these kind of Jacobian-free and matrix-free implementations of discontinuous Galerkin methods. And you can see here the purple line here in this graph is a implicit run without any preconditioning. And if you apply preconditioning, you can really cut down on the number of linear iterations quite drastically. So for details, please look at this archive preprint. Yes, so this is kind of what the code can do and what we are doing with this. Here are some earlier results on strong scaling. So you can see it's possible to scale up to quite reasonable numbers of cores, both for explicit and implicit versions of the code. Of course, this is not exascale here, but any mid-sized university cluster should the code should allow to quite use quite efficiently. Yes, so Tune and TuneFem. As already mentioned, Tune stands for Distributed and Unified Numerics Environment, and you could see it as a set of C++ modules for implementing grid-based numerical methods. And the development started around 2003, mostly, or actually only developers from Europe. Some of them have been there from the early days, for example, Christian Engwer, Peter Bastian, and myself, and then Andreas, Oliver Sander, and others joined later, and now the developers are spread around Germany, but also in Warwick, Lund, or in Oslo, Norway. And as mentioned, you can find some of the papers explaining the interfaces that we have designed, as well as a recent review of the entire project can be found online. In particular, the latest paper is open access and a good starting point for reading. So the main idea of this framework was to combine modularity, which I'll come back to in a second, flexibility and efficiency. And so flexibility, here the idea is that we separate grid structures and data. So at no time will you ever store any numerical data inside your grid implementation, which was the case in quite many codes at the time when we started. And the idea was to define abstract interfaces for each of the parts that go into a solver for PDEs, for example, a grid, discrete functions, and so on. And then, if possible, to base this on mathematical formalism. And just to give you here the take-home message, so to speak, one of the very strong parts in the Tune software framework is that we have a very well-defined grid interface, which you use to design your algorithms. And then later on, you can exchange the grid implementation with just a few lines, 2 or 3 lines in your code, to, for example, from a Cartesian grid to a completely unstructured simplicial grid and so on, without having to change anything in your application or discretization. And so these abstract interfaces work quite well even today, even though they're quite well established already, so about almost 20 years now. It still is quite a strong feature of the code. About the modularity, so when you're going to use Tune, then you're actually looking at quite a number of modules, of software modules that you can choose from. And of course, the main idea is that you never have to install the entire project for maybe just testing out some linear solver implementations. So if you're just interested in linear solvers, then you would only have to install the common modules, which give you some basic infrastructure, and then the iterative solver template library. On the other hand, if you're just interested in some grid infrastructure, you only have to install the common, the geometry, and the grid module. And then you can choose from a number of implementations of the grid interface. For example, here, a very recent implementation based on the pforest library, or a quite mature implementation based on AluGrid. And then based on these modules that you see here in the blue box, which we call the core modules, there is various application modules, for example, Tune PDE Lab, which is a discretization module also for DG-based discretizations. There is an entire separate project called the DUMOX flow and transport processes in porous media. You find the webpage here, which is based on Tune, but rather interested in just applications. There's even an industrial scale reservoir simulator, which is mainly developed by Sintef, Equinor, and Norse, as well as the OPM operations company. And you find the webpage here. So this is a drop-in replacement for the reservoir simulator Eclipse, which uses Tune technology inside. And then, of course, there is our module TuneFem, which is mainly developed by Andreas and myself. And here we're interested in implementation of discrete function spaces, some data management for adaptive and parallel simulations, and so on. And of course, Python bindings using Phoenix UFL to describe weak forms of PDEs. And based on this, we have our DG module where we implement this DG discretizations for these advection diffusion type problems. So a little bit more on TuneFem. You can find it, of course, through the general webpage, to our general GitLab page, and the tutorial, quite nice tutorial, which we also use for teaching, can be found here. And as I said, so we define some function spaces and functions in this module, discrete function spaces, discrete functions, and then quite a number of, let's say, infrastructure for automatically handling adaptation, parallelization, and load balancing. And the current focus actually for a number of years now has been Python bindings to improve the usability of the code. And of course, the question here is, can my students use this? And the answer is yes. So if you look at this little piece of code here, this is an implementation of a simple finite volume scheme for linear advection, which you could do in Python like this, using the Tune grid interface, which has been ported to Python almost in an almost identical usage. So you can prototype things with your students in Python, and then it should be relatively easy to port them to C++ for a more efficient implementation. And at least here at Lund University, we use TuneFem in 4 advanced, so master level courses, and it works quite well. As I said, there's also a tutorial, and there you find various examples, for example, virtual finite element methods, HP adaptive DG schemes for two-phase flow in porous media, moving meshes, other examples on adaptivity, etc. So coming back to our module structure here, we actually have other modules here that use all these infrastructure, for example, a moving mesh implementation done at the University of Stuttgart. Andreas has created an entire module for virtual element methods. I have some projects on droplet simulations. We have some space-time DG methods. And of course, most interesting for today is how could such a coupling to LandLab look like like to make use of all the numerical infrastructure that we have created here. So let's quickly look into how this could look like before we look into some examples. So when coupling with a land lab, we discovered, or when we started to look into land lab, we discovered that there is some difference in how you name things. For example, in land lab, what is called a node would be called an element in Tune, and the corresponding discrete function space in Tune would be a finite volume space. What you call a cell in land lab, we call a vertex in Tune, and then a corresponding space would be a linear Lagrange finite element space. And what you call links in land lab, we call an edge, or in particular the normal of an edge. And here the corresponding space would be a Rabiat-Thomas space with the polynomial order 0. So say we create a raster model grid in land lab with 5 nodes in each direction. How could that look like in Tune? So in Tune, we would like to have cells around. So these nodes in Tune correspond to the cell centers of elements. And to create a grid like that, we need the lower left and the upper right corner coordinates, and then just the number of cells in each direction. And so to compute that, we can simply extract the x of the nodes from the land lab grid, and then subtract here half a grid size in each direction, add it to the, so subtract it to get the lower point and add it to get the upper point. And then using this, we can create a grid in Tune that corresponds well with the raster model grid in land lab. And then, of course, we could carry out computations, and the question is, how do we transfer data? And this is, in this case, quite simple because the numbering is actually the same. So we create a node space, which, as said, is a finite volume space. Of course, the order here is 0, doesn't even have to be provided. And let's say we only look at one tracer, then we create a discrete function from that node space. And this could be transferred into a data structure living at the node in the raster model grid. And in this case, the data transfer is just a copying of the entries of this. These are both NumPy arrays, or actually in the case where we only look at one array here, we could even use the data structure given from the raster model grid. We could reuse that in Tune. In the case of 4 traces that we have been looking at in the beginning, it's slightly more complicated because we block the unknowns cell by cell. So we have a dim range here is now 4, n is 4. And in this case, we have to use some stride here to copy each of the tracers into the right position. So slightly more complicated, but still really, really simple. What happens, for example, to link data? So links in land lab correspond to edge data in TuneFem. But here we actually have to compute some index mapping. And I'll explain briefly why. So here we have, again, our raster model grid now with the links visualized, so the links between the nodes. And if we look at our grid in Tune, then you see these links cross an edge in normal direction, but on the outermost edges, we don't have any links. So what we have to do here is to identify interior edges in red. I hope you can see that. And then the outer edges unknowns belonging to this edge will just be set to 0 in our Rabiato space, and then this can be kind of, a connection can be made between these two structures. And as I said, here we have to compute some kind of link index map, which we have done and will provide, or this will be included in the TuneFem module. And then a copying of the data structure is again quite simple by applying the link index map here and scaling the links with the appropriate mesh size for each link, and copying it back, for example, to the link structure from TuneFem is the same operation by just dividing by the mesh size. So this is how, in principle, TuneFem can be coupled to LandLab. We can identify the grids and we can identify the data structure, and that's actually all we need to write solver modules for LandLab. And with that, I would like to hand over to my colleague Andreas to look at the examples that we have created with TuneFem in LandLab.
I think you have to start. Okay, already did that. Good. Okay, then let me just share my screen. There we are. Okay.
We see it, Andreas, just to make sure.
You're seeing, yeah. So you're seeing the yeah. So this is the tutorial where we sort of started off with looking at one or two examples of this. So we started here with the first one, which is this eviction example. Sorry, that's not what I wanted to. Sorry. Yeah, no, that's better. So this is the advection diffusion example, because as Robert already said, these DG methods are especially well suited for these type of problems, especially because they, as the one example showed, can be used without even a limiter for standard advection. Well, if one has some Burgers type term in the equations, then one does have to do some limiters to keep the method stable. So we thought we'd start with this method and also really just test how one could use LandLab data structures and combine them with the Dune data structures. So you can see the notebook now. So this is really just taken from the tutorial. Just cut out a little bit just to simplify it slightly, right? So we're taking here the grid and this advection solver TBD component, and then this is just the examples that were included in that notebook. Now, if I go here, you can say the only thing that we changed is that we now wrote our own component. This Dune advection solver. I'll come to these different parameters in a moment. So the standard version, if one doesn't provide any additional information, would just be a TVD limited reconstructed finite volume scheme with forward Euler and time. So exactly the same type of method implemented in the LandLab component. And then after that, everything is more or less identical. So one sets up the raster grid, mode grid here, then defines the corresponding tracers one would like to advect, and here the velocity, sets the corresponding values here, sets up the component, and then does the time stepping by calling update here in the same way as one does in the other case. And then at the end, one gets a very similar result. So we just look here at the maximum, for example, 0.95 approximately, compared here to also 0.95. So slightly higher maximum, so slightly less numerical diffusion apparently in the LandLab version, but quite similar. And then here is the component. Thought I'd just briefly to sort of walk you through what we had to do. So we defined the class deriving from this component. A lot of this is actually just cut and paste from the corresponding LandLab version. But then the main part, what we had to do is define the numerical model. This is exactly the code that Robert showed previously. So defining here the numerical flux function for the advection, given some advection field, and for upwinding, corresponding information about the actual velocity, and which we're not using here in this case, additional possibility to include diffusion, at least some simple linear diffusion, artificial diffusion. And then to keep physical values, we define that the lower and upper bound are supposed to be between 0 and 1. And then boundary conditions. So in this case, just Dirichlet boundary conditions, so just fixing the values on the outside to 0. Once one set up this model, then again, a lot of what's coming here is actually, again, identical to what we found in the LandLab version. So setting up these scalar values. This is actually just used exactly in the same way as in the other case. Extracting the velocity field. So on the links, so what we would think of as edges, so the normal component for the velocity on an edge, given by this field here on the grid. And then we defined here sort of a utility class, an adapter that does a lot of what Robert showed in the individual slides. So allows us to set up a grid, given the LandLab raster node grid, defining corresponding functions for the cell values, or what we think of the element values or the node values on in LandLab, and then the corresponding option for copying this back and forth, or as was pointed out, actually for a single scalar quantity, we could even just use the Python's buffer protocol to directly work on the same data. So here we decided to copy, and also provide the option to use actually the DG method. So in this case, on each element or on each node, we would be storing, for example, 3 or more degrees of freedom. So that's the way the DG method works, by blocking multiple degrees of freedom per edge for the different depending on the polynomial degree. So we decided there to say, okay, in this case, we would copy back only the average value in to LandLab. So in that case, one would have to one couldn't really change the data from the outside, because that wouldn't then correspond anymore to the DG version. But one can still visualize this DG data. So just as an example here, let's take this one. So this would now lead to a DG method without limiter. But was running code on the fly is, of course, always dangerous. Actually, restart the kernel just to be on the safe side. Nothing goes wrong. So as I said, this is exactly as in the LandLab code. Then we combine our component, providing additional information that we would now want to use the DG method. do the corresponding updating here. And as you can see now, the maximum is at 0.99, so very, very little numerical diffusion, which is the typical thing one would expect from a DG method. So this was the one example we looked at, and the corresponding code. So another example we looked at was this linear diffusion. So this linear diffuse overland flow solver, which was based around this equation here. So in this case, actually a parabolic equation, given that the velocity of the Q here is the velocity times the water height. And this is now the divergence of gradient of H. So this is actually a parabolic problem. And we decided to solve it slightly differently from what was done in LandLab. So we're using a completely implicit solver, or actually either a completely implicit solver. So here everything is evaluated at n+1, as you can see, or as a semi-implicit method where most of the nonlinear terms are evaluated at the previous time step, and the only the diffusion here directly is at the new time step. So again, just looking at what has to be done for the code, again, most of the constructor and what has to be done is very similar to what we found in the corresponding LandLab code. But of course, we need to define the model. So this is defined here. And as again, you can basically see this diffusion, nonlinear diffusion term now here. So given by the gradient of U plus the gradient of the topography multiplied by the height of times 7/3. So this is again UFL, a very symbolic way of writing everything down. So this is written down completely using this UFL. And the nice thing about the symbolic language is that things like computing Jacobians for these problems, as one would need, for example, for linearization or for implicit methods, is done on the Python level symbolically, and then we use that to generate the corresponding code. So again, the code basically is done exactly in the same way. So we can either use the linear diffusion overland flow router model component, or this new Dune one. And then the rest is again exactly the same as before. So read in this DEM map, construct the corresponding LandLab grid, which is given here, and then construct the possibly here the Dune component. I should add that, I mean, this was quite a quick implementation just to see what would be possible. The method is in itself not directly stable. I just give that as a disclaimer. So we're not quite at the same level as what the LandLab one can do. Hadn't expected to be able to do that in a short time anyway. So I needed to add a little bit of artificial diffusion into the problem to get comparable, stable results. But here you can see the time evolution of the flow. So it starts with strong rain, which then subsides. So rain goes to 0, and then one sees how the water collects in these low elevation parts of the domain. And this is the discharge. Again, I mean, here one sees, of course, differences between how the LandLab grid and the Dune grid would work. So these are actually still cells here for us. So we define the boundary conditions basically really on the edges of the domain. While my understanding would be that in the LandLab case, boundary conditions would be given basically here. So at this point, the water height would be forced down to 0, or would just stay 0. So there's of course differences between in the connection between the LandLab versions and the Dune versions, which do then also lead correspondingly to. So this is running the same thing in LandLab. You can see here that there's less due to the artificial diffusion. It's in the Dune code. I get much smoother results here, as one would perhaps expect. And there's a difference here also in the final discharge. So while I'm quite confident that we have exactly the same sort of outcome in the case here of the purely advection case, there's definitely some additional work that would have to be done in modeling the more complicated problems like this one. Okay. Switch back to Robert, then perhaps I think we only have the conclusions left.
Yeah, so that were the examples. And if you're interested in using the code, the installation on Linux or Mac OS should be relatively simple. The easiest way is to use a Python virtual environment that you could create simply like that, and then use pip install tunefem and tunefemdg or even tunevem, which takes a little bit, maybe 10 minutes, and then you're good to go. As I said, the Tune LandLab adapter will be integrated, let's say within the next week, and then we'll probably also put these examples somewhere if you're interested to try it out. If you're using a Windows operating system, then the best and easiest way to use the code is through the Windows subsystem for Linux, and then just follow the instructions from above. Yes, so this was all that we had on tunefem and coupling to LandLab today. The code itself is, of course, used in ongoing research projects. As I said, Andreas looking quite a lot into virtual finite elements. We have some work here on multi-phase flow based on Cahn-Hilliard-Navier-Stokes equations, preconditioning for atmospheric flows, Darcy-Brinkmann-Stokes for coupled flows, in particular liquid ice interfaces in collaboration with the group of Julia Kowalski from RWTH Aachen. There's some groups here at Lund that work with the code, PhD students Niklas Kotarski and Valentina Schüller. The group of Monika Eisenmann is looking into stochastic PDEs using the code, and then the group of Christian Rode working on moving mesh approaches for porous media flow. And there's probably quite a number of projects that I forgot to mention here. So if you're interested, please look at the web pages. The tunefem tutorial is a very good starting point. And of course, we thank you for your attention and are looking forward to discussion and questions.
Thank you, Andreas and Robert. We'll open it up for questions. I see Greg being happy. Do you want to go ahead, Greg?
Sure. So thank you for this really neat presentation. It's exciting. I have a bunch of questions. I guess One is sort of what are your thoughts on next steps regarding the LandLab coupling?
Well, as I said, so I think the first steps are made. It's very clear how to identify or how to kind of go back and forth between the existing data structures in Tune and LandLab. And now the only thing left to do is to identify problems that you want to solve and then trying to implement them in Tune. If you haven't implemented them in LandLab, I mean, it doesn't really make sense to rework problems that you have already solved. But if there are problems that you find hard, that appear hard to be solved in LandLab, then this would be a good starting point, I would say.
Yeah, I mean, so far we just focused, of course, on examples that you can already do, and probably, as I said, with the linear diffusion example, probably better than what we could do in this and in the short time that we have. But of course, there with Dune then would come other features possibly like grid adaptivity, perhaps different types of solvers what one could use. So as Robert said, it would be perhaps getting together and really identifying what Dune could offer in addition as a possible component to LandLab.
I think in the chat, Alejandro was asking a question about whether this is parallelizable on GPU units. So would you have comment to that?
Yeah, so not yet, but that's I'm starting to work on that. So we have put this off for a longer time because neither of us had really access to GPU clusters. And we didn't have any research projects associated to that, but it's of course a pressing issue.
I mean,
so not yet, but it's
so one thing we're really focusing on a lot on in recent time was more unstructured grids and things like local adaptivity, which in our case really means that grid changes, refines and coarsens throughout the full simulation. So dynamic, and that requires dynamic load balancing and that sort of thing. So combining that with GPUs is really quite a challenge and hard to do. So.
I think I had a question that one of the grad students in our group was trying to was implementing an ice flow model and like with a fairly standard assumptions like a shallow ice equation, shallow ice approximation. And he found that if he wanted to use like more triangular mesh or so in LandLab, that was difficult, and went to like another Python solver. Is this something that we should check out Dune for that too?
Yes, so we have quite a variety of mesh elements. So standard, of course, triangular, quadrilateral, or tetrahedral and hexahedral in 3D. There is some grids then also providing some prismatic or pyramid elements. And we even have implementation for very unstructured grids where you no longer have a reference element, so you don't really know what the geometric structure is other than you're given a volume and the number of nodes. So this kind of Voronoi type that can be handled, but of course then it's much more difficult to you're a bit more restricted to the type of discretization that you can use.
That's really encouraging. Thank you.
But there, of course, Andreas' virtual element method is quite a good candidate for these kind of complicated meshes.
As well. Yeah, I mean, so then, of course, I don't know if the student would be also wanting to work with things that are in LandLab, for example, or some other software solver. what made it easy, of course, and that's why we were focusing mostly on this one grid type. I mean, I know that LandLab has some other grid types as well, was that, of course, getting the corresponding numbering to work was fairly straightforward. That would be, of course, a lot harder in really unstructured grids. Not sort of impossible to do, of course. I mean, completely doable, but slightly more thought has to go into that. And
But there it looked like the hexagonal grids that are in LandLab are kind of a little bit like that. So there we would have to take a closer look.
Can I jump in with another couple questions? Did you check the performance in comparing like the advection problem? I'm curious to know whether the Dune solver was. I mean, you showed that with the right choice of well, with the DG method, you got a lot more accuracy and less numerical diffusion. I'm curious whether the solution was also faster.
So that's a very good point. So I think the advection solver in LandLab is a very good implementation. It was not so easy to come very close to that because we're in Dune. We have a unstructured grid interface, and even though we're using fully Cartesian meshes, a lot of the implementation of the scheme is not making use of the pure Cartesian structure. So to the quick answer here is our finite volume solver is quite similar in runtime as the advection solver in LandLab, but the DG solver is a bit more expensive. But then we have not done experiments where we look at how much runtime do we need to spend to get a certain accuracy, and so that I cannot answer.
The experience with things like DG is on the same size of grid, is going to be slower than a corresponding finite volume method, just also because it has a lot more degrees of freedom it has to work with. But due to the higher orders nature of the method, one can use coarser grids, so the same numbers of degrees of freedom would lead possibly to a better better solution, and from the runtime point of view, be still then quite comparable. So it's always a question if one looks at these methods on a fixed grid and compares the runtime, or for a fixed number of degrees of freedom, or for a fixed error.
Yeah, and I can imagine there's cases where the decreased numerical diffusion and increased accuracy is worth it. Like if you're doing, and like, you know, I was thinking along this because I'm a geomorphologist, I was thinking about topography advection. And there is a situation where you really don't want your topography to be melting away. Or if you have, let's say, layers of rock underground, you don't want their thicknesses to be bleeding into one another, because that loses a lot of valuable information. So I could see the case for
yeah. So there, the DG solver should be quite good.
Yeah.
And then, of course, grid adaptation could also help to increase accuracy without increasing runtime too much. But to maybe answer, so I think our finite volume solver was similar in speed, maybe slightly slower, and the DG solver was maybe a factor 4 or 5 slower than the advection solver in LandLab on this very simple example.
Right.
And there we maybe also have to look a little bit more into potential optimizations. But I wasn't 100% sure about the parallelization features of the advection solver in LandLab. So that is, of course, something you get for free in Dune. So both thread parallelization, which can be enabled with just one line, and then also MPI parallel execution is available without any modification to the code.
Right. That's an advantage.
With that, I think I saw Wolfgang complimented you on like how nice this has gotten together already in the chat, but he had to run and go teach. I think we asked the questions and we're at the top of the hour. So I wanted to like take the opportunity to thank you again, Robert and Andreas, for like doing this talk. And it sounds like it's really valuable, and it was impressive like how it's already connected in this like tutorial and example. So thank you very much.